The broadcast is now starting. All attendees are in listen-only mode.
Welcome to this IChemE Safety Centre webinar about PFAS risk, where it is and how do we manage it. My name is Trish Kerrin and I'm the Director of the IChemE Safety Centre. I'm joined today by Dr Matthew Askeland, who will take us through the issues surrounding PFAS in our environment. Before we start the webinar though, just a reminder for those of you that are here, obviously this is a Safety Centre webinar, though it's open more broadly to other people. We just want to acknowledge all the members of the Safety Centre. Without you, we could not do the work that we do in continuing to advance process safety. So thank you very much to our many members and also to our university supporting partners who we work with to try and advance process safety education at university so that we can start to get better results into the future as we work forward. Our speaker today is Dr Matthew Askeland, as I mentioned. He's a senior environmental scientist and PFAS specialist at ADE Solutions. He's been part of various state significant and Commonwealth PFAS contaminated land projects over his career. And he certainly has key expertise in practical PFAS solutions and how to develop and implement those. So I'd like to hand over to Matthew now, who will take you through his presentation today. If you have any questions throughout the presentation, please use the questions box and just type your questions in and we'll address those at the end of the presentation. Or if you've got any challenges throughout the presentation, you can use the chat box to communicate with me and I will then actually deal with that issue, or if it's a question, raise it as a question with Matthew. Thanks a lot, Matthew. Over to you.
Thanks for that, Trish. Good day, everyone. Matt Askeland speaking here from ADE Consulting Group. Let's see if that'll go up. Perfect. So here we are today to basically go through a really broad presentation on PFAS risk. So where is it and how do we manage it? So we're looking at this from a multitude of facets. So exposure to workers, exposure to people in their homes through food, the environment, and then also how it presents risk kind of on a corporate front and to businesses. So that's the first bit. The second bit, we'll just run through what are some of the common management practices and what are we using to control these risks currently in the environment and also conduct remediation where it's necessary. So I'll shoot on with that. I just wanted to note that ADE, I'm part of a PFAS team. There's a group of us who all work in the PFAS space, either on the analytical front, the regulatory front, or the technical front. And just a shout out to all the miners that I work with in that regard, who help us through these quite complex projects. So here's just the overview. We'll very briefly cover what is PFAS and the risk that they present. We'll quickly have a look at some lessons from the past. So what have we done to manage PFAS broadly and how did it work or not work? We'll look at balancing PFAS management strategies against risk. And then also we'll look at the ways to tackle these. So how are we tackling these risks? I'll also close off with the 4 pillars of PFAS management. So the 4 key areas that I see as key to managing PFAS risk. And then lastly, what are the top 6 engineering challenges presented by PFAS? Now, just as a small disclaimer, a lot of this discussion is around technologies and brands that are not my own. And obviously, I'm not the expert in some of those particular technologies and IPs that are owned by other people. So the opinions contained in this are my own and basically just provide a broad and conceptual overview. However, I am prepared to talk technical with people offline at any time. So really broadly, what are PFAS? And the answer I always give to people, obviously we've had discussions in the past about there being fluorochemicals. They've been in the news a lot recently, so everyone's aware of them. But one thing that people don't often talk about is that they're dangerously useful and they're incredibly good at what they do, and hence why they've been employed so broadly across industry and a variety of industries. So everyone knows about firefighting foams and AFFF. That's probably the one we hear about the most, where PFAS have been employed in various formulations in these firefighting foams and have been very effective at saving lives in doing so. But at the same time, there's a number of other applications such as coatings and platings, textiles, packaging, waxes and polishes, and a whole host of others that I just can't cover here. But we're not going to look too much into that. But the key risk is obviously some of these have been identified as toxic. They're highly persistent. they accumulate in the food chain, and probably most importantly, they're highly mobile, which we'll cover shortly. So there's one take home about what are PFAS other than some of them being toxic. While the jury's still out on the other numerous PFAS compounds that are out there, we have a few that haven't been established as having toxicity to aquatic organisms and effects on humans. But the real take home is that they are mobile contaminants, and herein lies the challenge for their management, that they have some very unique behaviors in the environment, that they're soluble in water, they're soluble in oils, or the organic phase, and this presents quite a unique challenge. They also have some strange behaviors surrounding micelle formation, hemimicelle formation, and bilayers, and this obviously changes the way we tackle them compared to your more traditional contaminants of concern, such as metals or other hydrocarbons. So just to have a quick look here, I'll talk occasionally about short chain and long chain. This refers to the hydrocarbon chain length. So this is the fluorinated tail, it's often referred to. Short chain versus long chain just refers to a shorter or longer tail. As far as hydrocarbon chain is concerned, typically those with the longer tail prefer to partition into the organic phase, and those with the shorter tail prefer to stay in the aqueous phase. If I speak about functional head, I'm referring to the functional group. Typically these are carboxylic acids and sulfonates, but there's a grand number of other PFAS out there, and we'll touch on that shortly. But these are kind of the flagship groups that have been studied. Everyone's familiar with PFAS, PFOA, PFHXS, and to a lesser extent, PFHXA, PFBS, and PFBA, which are the short chain congeners. These are short names that we apply to them, and the name generally refers to how long is the chain and what functional group is included. There are a number of other compounds such as precursors and fluorotelema alcohols, but these start getting a bit more complicated. So for the purposes of this discussion, we'll just be focusing on PFAS, PFOA, and then the shorter chain congeners, and I may mention precursors here and there. So we spoke about mobile contaminants, and this is where the risk comes in. When PFAS are liberated in the environment, they don't break down very easily. Those that do break down typically degrade from precursor compounds into other PFAS, quite often ones that are more toxic or have a higher toxicity. From when they are released, they have a number of mechanisms for transport. Probably the main one we hear about is water, so surface water runoff and then access to groundwater or surface water bodies. Less often we hear about air, so dust and vapors, which is kind of a new area that's being discussed more often at present. And then soil. So this is a mechanism that we're aware of, but we don't seem to talk about a lot, is that as we develop land or upgrade freeways, etc., we're quite often moving large amounts of soil around, which can actually act as another transport pathway. What happens during this transport is that these then reach sensitive receptors. So these can be biological systems, drinking water, stock water, etc. And this is where they unfortunately come in contact with those receptors. There's a whole other discussion to be had about transformation, precursors, and uptake. However, here we're focusing more on the technology and the pathways of managing it. But I can't understate enough how important it is to understand the pathways behind PFAS transport, because without a firm understanding and a good CSM, we can't really put in place the correct controls to manage the risk. And every site is different and presents unique challenges. So just moving on here quickly, PFAS in the environment. I'm primarily going to refer to these compounds that I mentioned earlier. This is just for the sake of simplicity. So PFBA, PFBS, and PFHXA constituting short chains, PFHXS, PFOA, and PFOS constituting the longer chains. I will note these are just 6 compounds over what I believe is a list fast approaching almost 7,000 compounds now. And there's just simply not time to cover all of these. And further to that, we just don't have the tox data on most of these. In Australia, our guidance really just focuses on PFHXS, PFOA, and PFOS. However, overseas, we do see emphasis on other compounds like PFNA, which is a 9-carbon long chain congener, as well as PFHXA. So the risk really is generated from PFAS liberation and it reaching endpoints such as agriculture, stock water, the environment, and drinking water. And these really breaking this chain is what the focus of this presentation will be on. So where is the risk? I mentioned earlier that we spend a lot of time talking about managing water and groundwater. We do manage our soil, and we are aware that transporting soil can migration pathways. However, we don't really look at the transport of the soil quite often as hard as we should. And then obviously dust is another one that I spoke of. So fugitive emissions and dust is one that we're only just starting to touch on to a greater extent at the moment. Probably not a major transport pathway of PFAS moving off-site, but for localized exposure to workers or people on impacted sites, there may be more to it. So who's at risk basically, or how do people get put at risk? Well, there's a number of pathways. The key ones being that when these pathways are complete, obviously it's the consumption of impacted water. So this could be humans and stock. Application of impacted waste streams to land. So this could be fill materials or soils, biosolids, so material removed from wastewater treatment plants to which PFAS have sorbed, and irrigation. So irrigation with recycled water which may contain PFAS. Direct exposure typically doesn't apply to such a great degree to humans and is more for the aquatic and some terrestrial environments. So this is fish living in impacted water or aquatic invertebrates living in impacted water. Consumption of impacted organisms applies across the board to humans and environments. With biomagnification, we tend to see higher PFAS effects higher up the trophic levels. Extraction and use of impacted groundwater, again, this covers stock and ecological. And then lastly, dust. So this one mostly applies to humans, but I'm sure it could be applied in an ecological sense as well to lung-breathing animals, which, as we know, tend to accumulate PFAS more. But inhalation is one that's been fully explored. So minimizing migration, no matter what the matrix is basically the key to managing PFAS, which seems very obvious, but historically we haven't been very good at doing this. So how do these impacts in life, how do these risks manifest, and what are the drivers for action? Here's a lovely photo taken not too far from where I live, at a river that's impacted by PFAS. Basically, there's the obvious endpoints such as degradation of the environment that is a key driver for regulators. Harm to humans via food in the environment. So we've seen some fuss lately around PFAS in packaging and other ways such as drinking water that humans are exposed. Exposure to workers. So these can be people who are working on sites that are heavily contaminated with exposure to dust. Impacts on stock and species of agricultural importance. So here in Australia, we have seen some fantastic cases where exposure to stock such as fish or cattle, as well as in the United States in the cheese and dairy industry, have rendered products unfit for human consumption. Devaluation of land and other assets due to contamination. So this can be the actual land itself, concrete pads, firefighting systems, places where these firefighting systems have been activated or foam's been used, in the case of AFFF, not to single that use out in particular, but basically devaluation of those assets, liability associated with polluting adjacent sites, so perhaps a liberation of PFAS on one site that's then been transported via groundwater, and then perhaps pumped out of the groundwater and irrigated with the neighboring site. So these can result in fines and prosecutions for breaches of legislation. Probably one that's notable here in Australia is the cost of major infrastructure projects and developments. So delays and added cost for managing PFAS, brand damage, director duties and liabilities, and lastly, breach of contract. So these are kind of endpoints where PFAS risk and how it impacts business, governments, and that are producing the drivers for action aside from just the knock-on health effects. As we mentioned, PFAS are used in a variety of industries. However, there are a number, unfortunately, that tend to use these more than others or liberate them in a way that is in higher volumes or higher concentrations. There are some benefits to these point sources, if you like, as opposed to diffuse sources, is that they are, while not easier to manage and identify. So these kind of primary industries include firefighting facilities of any kind, be they defense or training and maintenance facilities where hoses are flushed. There's a grand variety of things that fall under that, where PFAS are used in AFFFs. Defense bases, oil and gas, mining, and the list goes on. There's also another group of impacted industries, and I've actually left one out there, but that are kind of have secondary impacts, and those include infrastructure and developments, agribusiness, and utilities. So these are industries that essentially have PFAS coming from other primary sources and then have flow-on impacts from that, where they're not necessarily using PFAS themselves. We'll just shift on here. So I got one of my teams to quickly snap up some headlines. Recently, we had a massive class action around defense sites in Australia with up to 40,000 people suing the Australian government. We've seen a similar one recently for a different reason, not associated with contamination of land, but cultural loss being opened in the Jervis Bay area. And then I mentioned earlier, toxic forever chemicals contaminating plastic and food containers. Some that I didn't expect to see: Financial Review discussing PFAS as a ticking time bomb, when organizations basically look at the liability that they're sitting on, and then also the cost of cleaning up. And more recently, this interesting expose surrounding PFAS use in fracking sites. I haven't done much research into this one yet, but it is an interesting concept where PFAS could potentially be being pumped into the ground. So one to keep your eye on. Now onto the nitty-gritty. So really interesting is around quantitating risk for PFAS. There's a number of challenges. We've come a long way in the last 5 to 7 years around PFAS analysis and how we test PFAS in the environment, or test for PFAS in the environment and humans, or other receptors like biological receptors. Typically, this is done by LCMS, and we typically run these as trace or ultra trace suites, so looking at how big a microscope we apply to it, and there's a long or short suite. So these suites can be just simple congeners like the ones I discussed earlier, or a larger suite that contains precursors and all sorts of other things. There are some other tools out there that we typically use, like total organic fluorine, which aims to quantify the fluorine in the soil, and then through use of other techniques or by difference determine what percentage is likely to be PFAS. There's a number of leachability protocols we use, and this is in essence used to determine how mobile PFAS is in a solid matrix, such as a soil. So is it going to stay put, or if there's water ingress through the soil, will it travel with the water, and to what extent? There is some discussion if this is the best tool to be used at the moment. However, it seems to be the most common one. There are a number of oxidative assays for determining what percentage of precursors are in a sample. So this is taking a soil or water sample, oxidizing it, and then measuring the difference between pre-oxidative assay and post-oxidative assay to determine from those endpoints how many other species of precursors that weren't tested up here in this standard test are present in the sample. Passive samplers are something that are being explored currently. There's a variety of these out there. Still quite a new area, quite a challenging thing to do because of other environmental interferences. Leaf tests are just another simple way of measuring mass flux out of a solid matrix into water. So this is a good way to basically quantitate exchange between a solid and a water, and it's something that we frequently use for measuring how effective our remediation techniques have been at immobilizing PFAS. And then lastly, there's a number of sensors that are being developed out there. I can't speak too much on this technology because I haven't really spent much time with it. I know a lot of these are still early days, but all of these methodologies have some key challenges, and these include that basically in environmental samples, barring a few instances, PFAS are typically at very low concentrations. So we're talking micrograms to nanograms per liter, as opposed to milligrams per liter that we typically find for other contaminants. There's a number of unknowns, including precursor transformation. So this can be compounds that we're not yet aware of, as well as compounds that we're not yet aware of transforming into ones that we are aware of. Because of the low concentrations, as well as PFAS being contained in a lot of the products we use in the lab, in essence, a lot of our tests are susceptible to cross-contamination, either in the field or in the lab or through our equipment, and this results in false positives. Obviously, all labs are very diligent in making sure this is managed through QA/QC. However, it is still unfortunately one of those things that can happen. And lastly, some of the congeners, some of the PFAS compounds that we like to assess are quite challenging to quantitate. This can be due to basically their physiochemical behaviors, so how soon they elude interferences with other compounds. And there's a number of challenges to basically be overcome there in the future. So I just wanted to cover some really broad lessons in the past that are big takeaways from me for the last few years. I'm going to go through these pretty quickly. But one thing that's really important, I mentioned, is 3 compounds that we currently assess in Australia at the moment. In different states or countries around the world, this can differ. But not too long ago, we didn't consider any PFAS a risk. There's a number of different congeners out there, and some of those that we don't currently consider a risk may, in fact, later through toxicological studies, prove to, in fact, pose a risk, and we need to be prepared for this. This is not how we've addressed things in the past. In the past, we either said there was no risk, or we focused in on some compounds, then decided to go, okay, well, if the 8-chain carboxylic acid and the poses a risk, let's go have a look at the shorter chain. And then we've had to update our approach based on the behavior of that shorter chain, which we have now determined potentially does pose a risk. Probably an important point is that PFAS impacts do not always require management in the form of remediation. So we should really be looking, especially where there's low-level impacts, at other ways to manage PFAS rather than just remediation, even though remediation does play a key role. Again, leading on from point 1, a lot of matrices, pathways, and products we hadn't considered are likely to come to light. So in short, we've spent a lot of time on PFAS in water, or waters, PFAS in soils over the last few years. Now we're starting to look at fugitive emissions and dust. This was something that, if you look at literature, had a few mentions in 2010, 2011, kind of disappeared for a while and is now coming back. That's quite an interesting thing. So it's interesting to see where that leaves us. So leading on again from point 1 is that, and 3 is that management mechanisms need to be sufficiently future-proof. There's no point generating solutions that are only going to last a year before we have to add new compounds that they're not suitable for, or regulations change and they're not suitable. So we need to be looking to the future and going, what's likely to happen, while also not being hyper-protective. So there's no one-size-fits-all approach. The odds of one methodology for remediation or PFAS management fitting all requirements is very unlikely. So quite often what I'm trying to say is that there's multiple approaches needing to manage a PFAS problem. This is site-dependent and CSM dependent, so conceptual site model dependent. This one might ruffle a few feathers, but it's one that's kind of important to me, is that there's no use in developing approaches which generate a waste stream, which itself has an equivalent risk, or moves the risk from point A to point B. So digging up a whole lot of contaminated material that poses risk from a site and putting it in a landfill that's not capable of managing that risk does not make sense. Unfortunately, it's been a practice for some time. There's probably better ways to manage risk. And then lastly, migration management is important, in fact, very important. However, it's not the end all, and in my opinion, it's not a very useful tool on its own without source management. Source management is critical because if we aren't addressing PFAS at the source, we can be managing the migration pathway forever. We basically want to manage the source and the migration pathway simultaneously to address the problem. So I mentioned there's no silver bullet, there's no one-size-fits-all solution, and there's a number of unknowns and technologies out there. And the tendency here is to basically panic and either be too risk adverse and apply a great number of controls and be overprotective, or to ignore the problem and be underprotective. So there is a very important balancing act between proportioning how we approach a problem based on the risk. And that's something that in the early days of PFAS management, we didn't do very well. So an informed approach is the way that we should be approaching PFAS management to minimize risk. Basically, the right data is better than more data. Key to managing PFAS correctly is understanding the problem. So having a robust CSM, so site conceptual model, conceptual site model, and understanding what the transport pathways are and how we need to manage those on a risk basis. Once again, while remediation is critical in reducing PFAS risk, there are a number of other approaches that we need to take ahead, and that should be the last step. Typically in PFAS dialogue, we hear about studies, and the first thing people start talking about when we speak about a PFAS impacted site is treatment. Really, we should be looking at scoping, delineating, looking at opportunities to manage the risk without remediation first, before we're moving on to reduction and treatment. So that's basically dividing the site up or the material up, segregating it, and then deciding what needs to be treated and what can be managed. Some of the trigger levels in a few states in Australia as well as across the globe are quite low. Here, PFAS impacted soils, for instance, cannot be reused, and the trigger level for assessment is 1 microgram per kilogram, which basically means anything that is detected for our common methods here that we use to assess PFAS in solids is condemned without further risk assessment, at which stage we have to go to our regulator and have a discussion with them about how they see fit for this material to be used. So it's really important that we use an informed approach rather than jumping straight to the bottom here. And as we go down this chain, cost gets higher. It makes sense that we focus more of our attention on the low-hanging fruit that we can use to address the situation. So that's management mechanisms are a key way of managing PFAS. These I'll cover a bit later, and they are non-remediation mechanisms. However, remediation mechanisms or management mechanisms can really be split into two key groups, in my opinion. The first being those that address the source, so risk removal, versus those that address the migration pathway, so which I would see as risk minimization activities, but they don't necessarily take the problem away, they just break the pathway, so the source receptor pathway. So ultimately, what are we trying to achieve? Everything I will discuss either plays a role in removing the source area where PFAS was liberated, or managing the transport pathway to prevent PFAS impacts. So with that, PFAS moves basically through movement of soil and water. Soil typically has to be something mechanically done by humans, as soil, as we well know, mostly doesn't move by itself. However, water is a bit more tricky, and obviously the key pathway to monitor, because we have a number of different water sources on site, which can include processed waters, rainwater ingress, groundwater movement, and a whole number of other things. So management in soils, general approach, as we've covered, includes source removal or minimization of water ingress through the site. So this can be sealing a surface, minimization of transference to the aqueous phase. So this can be the use of sorbents and other materials, and mixing them into the soil to stop PFAS being transported out of the soil and into the aqueous phase, where it can be transported off-site to sensitive receptors. And unfortunately, a very typical method we have here in Australia right now is stockpiling, where material is basically stockpiled until we figure out what to do with it, which I guess at some points, that's the only option we have. So what mechanisms have we been using for managing this? Typically, dig and dump is a common practice, sending material, digging it out and sending it to a landfill for off-site disposal. On-site encapsulation, so using liners and impermeable barriers to separate PFAS from water tables or from rainwater ingress, which can be effective. How long-term a solution that is and how it manages leachate basically brings in various shades of how effective it can be. Activated carbon amendments in soil is another one that's been practiced. Activated carbon does have its place. However, reading through literature and being aware that it does have some limitations around short chain. And when we talk about solvents, we really need to discuss how reversible is the sorption of PFAS to that matrix, rather than just looking at things like surface area and iodine number, which in themselves don't tell us a lot about how strong the sorption is and to what extent it takes place. Specialized sorbents include formulations or mixtures which are designed specifically for PFAS or contamination sorption, such as Rembind and other competitors to that brand. So there's Fluorosorb. There's a number of them out there, and they have been specifically targeted at managing PFAS. Specialized physical encapsulation. This can include solidification. So this is the use of cementitious products to capture PFAS, which I'll touch on in a minute. Soil washing is one that's been explored and has had some success. I'm not too sure where it's at the moment with getting PFAS levels down to very low levels, but obviously this is a good way to remove certain PFAS congeners from soil. Thermal desorption obviously has been used a lot in the contaminated land industry for removing and destroying contaminants. The benefit of removing and destroying contaminants is that we no longer have the risk, and the risk has been completely removed rather than managed. Engineered carbon, such as biochars, is something that I've worked in extensively, as well as I understand that quite a number of papers are being published. Once again, similar limitations to activated carbon. However, there are some functionalities of biochars that are now being further explored. And then lastly, specialized encapsulation. So these are impregnated liners that could have a ion exchange resin, a activated carbon, or a specialized solvent such as Rembind or other, built into a liner. And these are wrapped around the soil or the solid, which could be a sludge, for instance, or a biosolid. And any material or any water migrating through that liner is then captured. So this is a new area that's kind of being explored now. There's a number of companies in Australia and abroad addressing this. So I've just dropped in a picture of what an operation for soil amendment looks like. This is provided courtesy of Rembind. In short, this is just trommel mixing of the sorbent into the soil. There's a number of bench trials and validation processes that go into making this a possibility, but the process is really similar for any other solid that's put in there to manage the PFAS. Keeping in mind that this is a chemical process, so it takes advantage of the physiochemical properties of the PFAS molecule to attach to the sorbents, essentially stick to it and hold it in the soil solution, the soil matrix, so that when water flows through the soil, it does not move into that aqueous phase and proceed into groundwater, etc. One that we've been working on developing is Ambiolock, which is a physical method. The aim here is not to exploit the chemistry, but instead of stopping the PFAS moving into the water, we're stopping the water getting to the PFAS. The goal here is to also produce something useful. So through producing concrete from PFAS impacted materials, we can stop water moving through the solid phase and transporting the PFAS out of the matrix. And obviously the PFAS is trapped physically in the concrete as long as the concrete is solid, and it can be recycled and reused. Waste and leachates are another real interesting one. Obviously there's significant risk surround managing our wastes and these entering leachates and how we manage those leachates from landfills. The general approach tends to be capture and disposal or capture and retention. Mechanisms that we can use to manage this include permeable and impermeable landfill liners. So I spoke about the liners that are on the market previously. These can either prevent the flow of water and channel it to one area where it can be managed by a water treatment plant, or a flow-through system that allows gated flow-through or total flow-through across the entire landfill, where PFAS can be basically absorbed in the liner itself by a special solvent. Leachate treatment systems using water technologies, which I'll cover on the next slide. So there's a number of systems out there that seem to have had great success in leachate, which is quite a complex matrix. So kudos to the teams that have tackled that problem. Incineration of leachates and wastes is another approach. Quite ironically, disposal to a wastewater treatment plant or liquid waste facility for leachate is a common practice. Retention on site is also a common practice, so basically ponds. And then again, direct disposal to licensed landfill for biosolids. So looking at the points on wastewater treatment plants and disposal of biosolids, there's kind of a loop there because you have PFAS leaving landfill and leachate going to the wastewater treatment plant. PFAS at the wastewater treatment plant binding to solids, and then in some cases, biosolids are applied to land, as I mentioned earlier. However, in other cases, it's disposed to landfill, where it again enters the leachate, and we have to continue managing it in that cycle. So that's an important and interesting point. So management in wastewaters. I'm just quickly running through these, and we'll get on to some other items after this. So how can we manage PFAS in wastewaters? Source tracing is a key one, and trade waste management. So finding out where our PFAS sources are that are coming into our wastewater. Because obviously wastewater treatment plants typically don't tend to generate their own PFAS, they come from other sources. Impacted material segregation applies to biosolids, so finding out if we do have, through our monitoring programs, an excess of PFAS at a given time to separate out the biosolids generated during that process. And there's a number of other removal techniques, including reverse osmosis. These are expensive techniques, and with the volumes of water that are generated typically by wastewater treatment plants are not often practical. There's a great number of technologies that are being investigated or are currently being applied. So one of them that I mentioned, foam fractionation, has had really good success with managing leachates. So some of these do apply to managing leachates, but also groundwater contaminated sites. Has the advantage of not generating waste in the form of spent resins or activated carbon or similar other solids, but instead just a concentrated waste stream. There are also a number of resins and activated carbons and sorbents that are quite effective. Unfortunately, these do require disposal as a solid, or then can be destroyed by plasma arc or something similar, or incinerated. One of the key areas that we're looking at the moment is in situ treatment and mobile treatment on a small scale. So referring to source tracing, a lot of the trade waste or those groups that are producing trace amounts of PFAS that contribute to the diffuse source entering wastewater treatment plants, the contamination could potentially be better managed on site, so upstream, rather than trying to manage it at the source. And I think that it's fair to say we're going to see more regulation in this regard in the future, but we'll wait until we get there. There are also a number, just while I'm on this slide, a number of other solid resins and polymers that are used, typically in oil and gas. And I guess their function is that they have a smaller footprint, and the plants can be smaller than a loose bed resin. So number of providers here, number of service providers with unique technologies that all have their own benefits. There are some that I didn't mention here, like zero valence iron, metal organic frameworks, and then also there's some work being done in electrochemical oxidation. These are methods that I haven't seen rolled out on a large scale. I've seen in literature. So typically where we're aiming at the moment is pump and treat with activated carbons or resins or polymers. So these are the primary kind of methods we use to remove PFAS from water. Of course, this is not the source addressing way to approach things. This is a management process, managing the transport pathway. Surface water is a similar case. This is a management approach rather than a remediation approach. Well, it could be argued in the case of groundwater pumping out plumes and removing them is a remediation approach, and it technically is. If the source hasn't been addressed, we'll be there for a while pumping out water. So a typical approach is capture and treat, at-site water management and monitoring. So site water management can mean diverting water away from areas that are known to have PFAS impacts and putting in place management practices that reduce the generation of PFAS impacted water, such as covering stockpiles, etc. There are a number of products out there. So there's Aquagate, which is a sorbent that can be put around the edge of ponds, and water can be allowed to flow through it and will capture the PFAS. There's a number of mats that can be placed under waterways to protect them as well from intruding PFAS impacted groundwater. There's geofabric options such as socks and the membranes I spoke about earlier. But quite often we tend to capture it in ponds for either disposal or treatment. And then I mentioned diversion away from impacted materials, or just use of impermeable barriers as a management technique where essentially something like sheet piling or physical barriers can be put in place to stop water reaching a pathway where it could impact either human health or groundwater or the surrounding ecosystems. And groundwater is quite a similar thing to the wastewater that I discussed. Key ones that I wanted to highlight here are injection technologies, so such as colloidal carbons. There's a few nanotech options here as well. And then also physical barriers, stopping the groundwater from flowing to places we don't want it to go. So these form, again, under pump and treat. Phase exchange, which kind of forms pump and treat, so taking it from a liquid to a solid phase. In situ plume immobilization, so this can be an obstruction of movement of the PFAS plume. And then lastly, monitoring is a tool that we also use to kind of inform the suitability of those approaches. While PFAS has been removed in most cases, or at least PFOS and PFOA and PFHXS from a lot of applications, there are a number of precursors and possibly other PFAS compounds that may be still used in foams. Just looking at the firefighting example, there are other applications where PFAS is still in use or allowed, and obviously this varies all over the globe. However, there's some real critical considerations for managing risk that we need to consider in areas where we have to have ongoing use. So this includes obviously disallowing all unnecessary uses, point one, but also ensuring that there's very astute consideration of the transport pathways, and just using AFFF as an example. So if we have to use it, that we've put in place a way to understand where it'll go and how it'll be managed and what the possible receptors are if that risk isn't managed. We need to manage waste and emissions produced by industry. So this can be gaseous emissions, dusts, a number of other things. We need to have in place suitable monitoring programs where PFAS use is essential, that will basically notify us where we aren't meeting the requirements for managing the risk, i.e. there's measurable migration off-site or open pathways to receptors. Have in place specialized contaminant infrastructure, so impermeable pads, water holding tanks, treatment systems, etc., etc. And then lastly, have in place a response to emergency discharges. So if we do have a hanger that discharges foam or a plating facility that has a leak, have in place a response as part of that site's management for dealing with those events. So basically they can be addressed before the plume migrates too far and becomes a much larger problem to manage. So onto my 4 pillars of PFAS management. These are basically the key issues that I see as addressing PFAS risk. So the first one is understanding the problem. So this is looking into the extent of contamination and the risk associated with receptors, and then developing a really good conceptual model of those transport pathways and deciding, can we manage this problem or does it need remediation? So do we need to do anything? If we do need to do something, can it be managed by changing our practices or putting something simple in place to address this issue? For instance, an impermeable covering, changing or diverting water flows, or how we dispose of wastes, or do we require remediation? If the answer is we do require some kind of management, right? Does the PFAS need to be managed? And to what extent is that management required? And then derive aspirational targets. So the reason this is an important one is we need to make sure whatever we're putting in place is sufficient to arrive at those targets, whether it be mass flows off site that we're addressing, or concentration we want to have in the discharge water. Those will be the things that guide the decision, the technologies we employ, or the group of technologies we employ to address this. Again, remediation first management, basically comparing whether we can achieve that target just through management practices, or if there really are or is a need for remediation. And then lastly, something we don't often look at is feasibility. While there's remediation technology out there, if the plume, PFAS plume, for instance, is in the CBD under a number of buildings, digging up the soil and treating it might not be a possibility, and that may then defer us to other technologies that we have to use, such as pump and treat. So it may be decided for us which application we have to use. Further to that, obviously there's budget considerations, but we won't go too much into that. And then lastly, suitable application to tools. There's no silver bullet. We do have to be careful of trying to use one approach or use a hammer for everything. Contaminated sites more than often require more than one strategy, typically a source removal strategy paired with a management strategy for groundwater or waters. And then don't underestimate PFAS management plans. The fact that these small management plans can assist further with managing PFAS on site. So how do they help? Basically, we can change the way we work on site to reduce PFAS impacts and risk. This can manage the spread of PFAS, and these can be as simple as having practices in place for how we treat water and use water on site, wheel washes, segregation of stockpiles, or the order that we work, working from less contaminated areas to more contaminated areas of the site, or taking into account aquatards. So there's a number of things that we can do that reduce the risk of the actual physical works or how we operate on a site. Further to that, spoil management. Adequate spoil management stops impacted soils being reused. And unfortunately, in Australia, we've seen a number of cases where impacted soil has been reused, and then those sites have had subsequently needed to be remediated. Ensure soil receives the right treatment. There's no point in over-treating soil. And then lastly, saves money and time. So if we know what soil is being treated where, we can really streamline our projects. Water management I kind of covered. But in essence, these can be simple things such as drain diversion and how we treat water on site, including processed water to prevent spread of contamination, such as reuse and dust suppression, but also to reduce costs and streamline management. And lastly, OHS management, including PFAS management plans, protects our workers, takes into account any special circumstances of the site, such as dust generation, really high levels of PFAS, like we see in some firefighting training areas. And controls can be industry standard. The things that we can implement here to protect workers don't have to be terribly complicated. P2 dust masks or equivalent to prevent inhalation, and good hygiene practices such as washing hands after dealing with PFAS impacted materials. So PFAS in air and vapor is really one that we don't talk about a lot. So I'm going to whiz through this, but it is an emerging area that needs to be discussed more. So some species of PFAS can exist in vapor, other species attached to particulates. Most of the investigations published so far deal with household or office dust. However, little data deals with occupational exposure to workers on PFAS impacted sites. So this can be in hangars or confined spaces such as engine bays or engine rooms that had firefighting foam systems activated, on chemical manufacturing facilities, or just in general dust during earthworks on site. So basically, we're looking at confined spaces, pits and utilities, aerosols, and material disturbance. So this is something that hasn't been discussed. Here's just some, pictures of people working in dust, just to give you the idea. If this surrounding material is highly PFAS impacted, odds are these workers are getting exposed. Once again, the remedy to this is fairly simple. But it's still something that hasn't been discussed to a large extent, and then also fugitive emissions moving across site boundaries. Here's some interesting pictures of some PFAS dried on a concrete piece of ground near a maintenance facility, just to show that basically this is scuffed up or is disturbed. People will be breathing that in. So just being aware of time, what are the critical challenges that I see for the future? In short, it's really important that chemical engineers work on developing apt analytical tools capable of measuring PFAS in the environment in relevant matrices. So these include concrete, biotic matrices, and obviously waters, soils, and all sorts of other things, to allow us to better understand how PFAS behave. Because having these tools will basically inform regulations. So the example here is the example I used for sorbents. If we're going to use iodine number and surface area or specific surface area as a measure for how well a sorbent works for everything, that's not an appropriate measure to look at sorption, desorption behavior, and is not applicable to a heap of other PFAS compounds. So really, we need to look for better ways to measure things in the environment. Are there better tools than ASLP? Are there better tools than these indicative measures that give us more dense information about what we're actually doing? We need to pioneer ways to innovatively manage our wastes and end-of-life products to reduce PFAS mass flow to the environment. So this is either removing PFAS from those wastes or looking at spoils, waste, and unwanted AFFF and how we manage it. So rather than throwing in landfill, are there better ways? And if it does have to go to landfill, how do we manage those risks there? This is a really important one and applies more to infrastructure and large-scale civil projects, but we need to engineer technologies that allow safe reuse of PFAS-impacted materials. Treating all PFAS-impacted materials as condemned rather than a resource is not a very sustainable way to do things, and quite often is not validated by the risk itself. Development of suitable AFFF alternatives is one that we hear about all the time in the industry. This is a key challenge to basically find a way to produce foams or firefighting adjuncts that will keep our communities safe without the environmental contamination. And I think that's been echoed really largely throughout the environmental community for some time. We need to consider novel investigation and management approaches to minimize impacts on projects. So this is a upstream way of looking at PFAS management and basically rolling out the enviroengineering aspect of site assessment before doing design work and civil work to basically make sure we aren't building bridges and tunnels up through the middle of PFAS contamination and then figuring out how to solve it after the fact, which typically ends up being more expensive and a regulatory nightmare. And then lastly, structured technologies need to be developed, which are basically cost effective and allow PFAS reuse of those materials. Excuse me. So where reuse is not a sustainable method. So we need to find ways to manage PFAS or destroy it at an acceptable budget. And that's it for me. So
Great.
Any questions?
Thanks for that, Matthew. Yes, we've got quite a few questions come in, so I'll start from the top of the list. The first question is, are sensors being developed for real-time monitoring for PFAS?
Yep, so there's a group over in the US, one in Australia and one in Norway, that are developing slightly different technologies. Some of these I've seen have been developed as a snap pack, more for just the present absent. Obviously, that has limited utility. There are some sensors that, yes, are flow-through technologies and designed to basically send an electronic response to a receiver that's calibrated to basically suggest what concentration that would be, how sensitive and how viable those are with other interferences. That's yet to be seen. But yes, real-time monitoring is potentially the goal here, and that would be incredibly useful with drinking water treatment systems. So looking at the efficiency of our treatment systems, whether it works out with co-contamination, I guess that'll be seen, but it's still a very interesting approach, and I'm very keen to see where that goes.
Okay, great, thank you. So another question, treatment can be extremely expensive, particularly for low-level concentrations. Do you see options for soil and or water offset where off-site remediation, for example, stream bank erosion repairs, could be applied that could have larger environmental benefits than pouring millions of dollars into treatment?
Yeah, I think this comes down to more of a risk assessment question. So when we look at, in Australia, the method we use for making this assessment is looking at the leachability. So if we're going to throw something away that's, 1 microgram per kilogram, which could have a maximum leachability of around 2 micrograms per liter, it comes down to assessing the transport model, so dilution and attenuation, or at least dilution factors, and whether it poses a risk in that new location. Considering how widespread PFAS are, we can't take it all and put it all in landfills or destroy it all. It's not possible. So we absolutely do need risk measured or at least risk considered methods that we can go and reapply this low level material. So whether it needs to be on a riverbank, maybe that might not be the kind of risk that we're willing to accept, but building an embankment to a road, there's a number of applications where we can minimize the risk or put a clay capping on it if we even have to use it.
Okay, thanks. The next question regarding new technologies. There is a waste stream associated with the regeneration of the media and the overall waste with contaminated carbon, resins, etc. Is the industry looking at the reduction of waste, as there is a significant cost to the client to remove the waste off-site?
Yep, absolutely. I think this should be a key focus, and I mentioned in one of my slides, unfortunately, I don't see much point in taking PFAS that's in the environment and then moving it from A to B, or concentrating it on something that in itself requires management. So 100% agree, and it should be a huge focus. I know there are a number of groups that are focusing on the destruction, so either the desorption of these from these resins, and recharge or reuse of these, such as resins or activated carbons, and in situ destruction. And then there are technologies out there like foam frac, which don't generate these kind of wastes, concentrate the waste stream, and then basically can send a much smaller volume off for destruction. So there's a lot more sense in treating a smaller volume or destroying a smaller volume via incineration or plasma arc than there is obviously a much more diffuse source. So tens or hundreds of litres versus hundreds of thousands of litres.
Okay, cool. Is it possible to conduct a HRSC, in brackets MIP or OIP, on PFAS contaminated sites?
It's a hard question. I guess all this comes back to, it depends on the congeners. So there's a lot of PFAS that we have some tox data on to make decisions about, what the risk is to people on site or receptors on site. But there's also a number that we don't know. We just don't have the values that we need to make those kind of quantitative assessments. Mm-hmm. So human risk and environmental risk at the moment is, I think wishy-washy would be a strong word, but it's a very difficult thing to do, and it's basically based off guidance that we have from either state governments or federal governments, and what they call as trigger limits, essentially. But it's not based off an actual quantitative assessment on a case-by-case based on toxicity data.
Cool. How about enzymatic defluorination for PFAS?
Yep, so there's quite a few defluorination technologies out there. ACOM's got defluor and a few others. Like plasma arc and a few of the other processes we have, question comes down to cost and throughput. So yes, we can build a massive plant. So it would be great if we could go to, say, a wastewater treatment plant or a pump and treat facility and just destroy all the PFAS. But when we're talking hundreds of thousands of liters and or large flow rates, it very quickly becomes infeasible. So that's where methods that concentrate the PFAS, desorb the PFAS, and allow destruction are great. Defluorination does provide potentially some good options. As far as biological methods go for defluorination, I haven't seen much merit in these just yet. Mm-hmm. But I mean, if anyone has any more info on that, I'd be very keen to see it. But one of the questions that some contemporaries in this area have asked is if we're talking about a biotic method, those bugs have to be pretty desperate if they're going to cleave a fluorine instead of a hydrogen in the environment. In a controlled system, possibly. And yeah, if someone has more information on it, I'd love to hear about it.
Okay. And the last question, because we're almost out of time, have you looked into the MyCellX technology to remove all PFAS analytes to non-detect, and what are your thoughts?
My thoughts on MyCellX is I haven't explored it myself in the lab. Given the opportunity, I'd love to. Like many of the resins, has great merit. It seems to be used, so the company that owns the technology has been putting it out there and holds the IP quite close to their chest. So I'd love to hear more. But yes, I think it's great. And one of the major factors that I think is great about it is that it can deal with co-contamination. Other oil, like oils, hydrocarbons, and other contaminants that typically need to be pre-scrubbed out of effluents before treatment. So that's a massive advantage alongside a smaller footprint. So would love to be able to work more with that and learn a bit more about MyCellX, but I'm not really sure how it works.
All right. Thank you so much for that, Matthew. We had a great number of questions and some really interesting questions in there. That presentation was fantastic, and I certainly learnt a fair bit about PFAS from my own perspective as well. So thank you very much. We greatly appreciate you taking the time to deliver that presentation webinar for us today.
No worries. No worries. Thanks for having me.
You're welcome. So we've got some upcoming webinars in the Safety Centre as well. There's a range of them on the screen now. You can check out our website link there for any details that you may and where you can register from them. Not all of them are up on the website yet, so just keep checking back and we'll see how we get you registered for those. We run these webinars on quite a regular basis, and the idea is to continue to keep everybody informed of what's going on. This webinar was recorded and it will be available on our YouTube channel later today. So you will be able to go and look up the IChemE Safety Centre YouTube channel and access this webinar for further sharing within your networks as well. So without further ado, I will thank Matthew again and sign off from the webinar. Stay safe.